Okay, great. Yeah, thanks. Good morning, everyone, once again. And thanks for joining us for the final day of the Summer Institute. And thank you for the introduction. What I have planned for this session is to just give you an overview of some of the work that I've been doing broadly in the field of network science. And I think if you've read the snippet of this talk, I'll try to focus a little bit on one specific type of network problems that I'm particularly interested in, which is the idea of inferring social influence or peer influence in large social networks. So I'll try to spend more time on that aspect of networks. So before I start, I thought I'll try to switch my more traditional self-introduction with maybe giving you a network introduction of who I am. So this is a plot that I generated. It's one of the first network plots that I created almost 10 years back now. This is me, right at the center. And I mean, you can see how it's not a very sophisticated visualization, because back then we didn't have too many tools. But I mean, if you just look at this visualization, you can kind of picture a lot of my friends clustered by their organizations. All right. So you have, for instance, some of my school friends here, back where I come from, some undergrad and master's friend from here, just one you probably somewhere in one of those clusters. And then I have some friends from my workplace and intern. And again, like the reason I'm showing you this is two reasons. One, it's a very simple way of thinking about what social networks lets you do. It lets you visualize these communities of different relationship types. Second, this network was actually constructed using the Facebook friendship network. And you could actually plot this back in 2010. You can't do this anymore because the Facebook Graph API is a lot more restricted. So to plot this, you actually need to know who your friends' friends are, and you wouldn't be able to access this data now, publicly at least. All right. Okay, so for the next 1 hour or so, this is what I have in mind. So first, what I'll try to do, and this is perhaps my chief aim for this session, I'll try to discuss the theoretical and practical use of studying networks. Right. So over the course of the Summer Institute, you have some exposure to other aspects of computation social science, like NLP or analyzing online news, etc. So I'm going to try and make the case for why you should also learn how to analyze social networks and how that can be useful to your area of work. And again, as I mentioned, I'll try to spend some time talking about this specific part of network analysis called influence estimation, which I think might be useful to some of your work. So I hope that this is interesting to you as well. Okay, so I generally start my network presentations with this particular example. And if you've heard me speak about networks, you've probably seen this slide many times. Have any of you not seen Game of Thrones? Right, and I presume that some of you probably, okay, you have the answer hasn't seen Game of Thrones. Okay, I just naively assume that everyone has seen Game of Thrones. Most watched TV series of all times. So this is clearly a network, right? So you have nodes who are characters in the show, and there are some links between them. And what do you think these links capture? And I mean, if you've attended the previous summers, you probably know the answer. So you're not eligible to answer. But any guesses for what these links between the characters are encoding in the social network? What is this network of? I mean, if you squint really hard, you might be able to read it off the lines, but I'm hoping you cannot. What's that? Relationships? What kind of relationships? Family relationships. No, so actually, I think the family is color coded. So you have the house symbols here, but that's the family is a node attribute, right? But I'm asking what would the links capture?
Co-occurrence in a
Co-occurrence. That's a good answer. That's not what's happening there. So the two actors who co-occur in a particular scene, they can be connected. Yeah. The conversation. Yeah, it's similar to that, right? So you can co-occur and have dialogue, and maybe you have a link between the two. Not what's happening here. Any other creative guesses?
story.
Who killed by whom? And romantic. You clearly haven't seen the show. But But that's a good answer. You might who gets killed by whom? Yes, that's actually closer to what's happening here. This is a betrayal network. So who betrays whom in a social network, right? And the more the thicker the lines, the stronger the impact of the betrayal, right? So if there's a really thick line, so you have Ned Stark here and your Peter Bailey. The Peter Bailey directly contributed to the assassination of Ned Stark. So that's why you have a really thick line. What are the dashed lines? So there are some lines that are dashed, right? And some lines that are bold. Yeah. Yeah, so it's like the betrayal is implied, not right? So this is a really cool way of thinking about how you can actually encode multiple different types of information in a graphical representation, right? So even if you have like if someone like Lance has not seen the show, just by staring at this for a very long time, you get a gist of what's going on in the show, which I think is pretty cool thing to do from a representational perspective, right? So again, let's go back a little bit. Like Game of Thrones, our society also is composed of several independent components or entities. And then, I mean, relationships in kind of this network can often be based or created from interactions. So again, this is not a network of social relationships like the previous one that I showed you. The links here are actually constructed from interactions or from behavior, all right? So these kind of interactional networks are getting increasingly popular in the field as compared to the pure relationship networks. And one reason for that, of course, is it's getting increasingly hard to access high quality relationship networks. So you can't do it off a public API on most platforms anymore, right? So to take you back a little bit, even though Game of Thrones is a very recent example, the field of social networks has come. And some of the early works in this field actually come from the early 18th century. And so again, if you have attended any course on graph theory, you might have heard about Euler's seven bridges problem, where I think the problem was how do you visit all the land masses here by traversing each bridge exactly once. And so what Euler did was he showed that there is a very simple condition that needs to be satisfied for the existence of an Eulerian path, an Eulerian circuit. Right? Around the same time, there was a person called Pierre Hoover, who's a Swiss naturalist. Around the same time, like 1736 and 1802, who's actually published a thesis which had a chapter on the dominant structures of bumblebees. So I don't know if you have observed bees, but bees actually have pretty sophisticated social structuring. They have roles within their family, and then based on your role, you have specific activities, specific lifespans linked to that. So it's very structured. And so in 1802, he published a thesis where he had a chapter specifically focusing on dominance network among bees. And arguably, this was the first ever published empirical work on a network. And again, it's a network of bees. But I think this then spurred further discussion on the topic. So my point of showing you this is to point out that the study of networks goes back at least 2 centuries. Right? I mean, the systematic study of networks, there's conceptual discussions on networks predate this as well. So if any of you are interested in just understanding how the field has emerged from then to right now, 20th century, I heavily recommend this book by Linton Freeman. It's available in US library. I think it's a PDF of this online as well. And it's a very small book. You can read it over a weekend. It's a very, very good source if you want to is curious about some of the early work in this field and how the field has progressed so far. So one of the reasons why, again, I am personally very excited about social networks, and some of you are here, is because network structures are universal, right? So you have networks from 82 centuries back, which show similar network structures to the kind of networks you study on Facebook or TikTok or any other online platform today, right? Even though they're completely unrelated contexts. And so I'm going to give you a very extreme example of this. So this is from a study that was published in 2010. I think in Science, probably in Science, yeah. And so this is a study which was done by researchers at Oxford and Hokkaido University in Japan. It's a collaborative study. And it's actually a very interesting study. So what they did was, I don't know if you know about slime molds. The slime molds are unicellular organisms, single-celled organisms. Latin name is Physarum polycephalum. So I mean, you might be able to see a slime, even though they're single-celled. They're big enough for you to see with your naked eye. So if you, after a heavy shower, if you go out, you might see like these rotting pieces of wood, on trees, and you might see like this yellow slimy thing. So those are slime molds. And slime molds, so this is a slime mold here, right? This yellow dot over here. So what the scientists did was very interesting. They wanted to culture a slime mold. So they took a slime mold, put it in a petri dish, and they sprinkled oat flakes in the petri dish. So oat flakes apparently are a slime mold elements. They like oat flakes. So they sprinkled oat flakes in the petri dish, and they tried to study how the slime mold actually forms food tunnels to access those oat flakes, right? Now, what you see here in the subplots are, this is the slime mold, these white dots are the oat flakes, and this is the slime mold kind of expanding to connect to these oat flakes, right? And then you see over here, it's 0 hours, 5 hours, 8, 11, 16, and 26 hours. So it kind of spreads out indiscriminately, right? And then over time, it removes some of these non-useful fats and solidifies some of the tunnels connecting to the oat flakes. And so by the end of 26 hours, you see there's this slime mold, again, just to remind, a single cell organism that is being able to connect to all these oat flakes using really strong non-redundant connections. All right. This is pretty cool, right? Even if I didn't tell you anything more, this by itself is pretty interesting because again, a single cell organism is able to form food tunnels pretty efficiently in just 26 hours. Now, what I did not tell you, which is perhaps the more interesting part of the study, was that the researchers, when they placed these oat flakes, didn't do it randomly. So it didn't like sprinkle the oat flakes. This was done according to a pattern. And so what they did was actually, they coincided the location of the oat flakes to match with the location of cities around Tokyo. So the oat flake network mimicked the relative position of cities in and around Tokyo. All right. And so what they were actually able to show was that the efficient food tunnel network that the slime mold was able to construct in 26 hours mimicked the actual Tokyo rail network pretty well in terms of the structure. Right. So again, this is really impressive because it basically shows that following very simple heuristics, small organisms able to create a network that shows a lot of similarity in network structure to something that arguably took decades to build. Right? And so this is what fascinates me about network. It's the idea that you see similar structures reoccurring in contexts that have nothing to do with each other, purely because of similarity in the underlying mechanisms. Okay? So the other thing, of course, that I want to point out is that networks are not always directly observable, right? So sometimes you have to construct networks as a representation from things that you see or from the data that you use, right? So then this is a good example of a constructed network, and this is actually a network where the characters are connected based on co-occurrence in a scene, right? So if the two actors in a movie co-occur in a scene, they're connected. The frequency of how often they co-occur is the strength of the time, right? As you know what movie this is, right? It's Lord of the Rings. This is, can you guess what movie this is? People looking at the character names? Godfather, yes, right? Again, just by staring at these networks, you might be able to tell something about these movies, even if you haven't seen them. So these are multi-character centric movies. That's multiple key characters. That's why you don't see any one node really standing out, right? But then if you do something similar with, say, this, right? No, this movie, this is Schindler's List. So you can see it's a very clearly like an egocentric network. You have one common high centrality node, and then the other nodes are kind of spread out around it. Similarly, this is Forrest Gump, and again, this is co-occurrence network. And again, it's very clearly an egocentric network. It's focused around one central character. So again, these networks, the relationships here are not directly observable. As this is something you are constructing based on data from a script. Right? And this is the final example I want to share with you. And this is from a paper, it's Scientific Reports 2011 from Varavasi group. And the paper was on something called the flavor sharing hypothesis. The idea that when you're cooking, if you use ingredients that share flavor from compounds, you end up making better dishes. That's the hypothesis they wanted to test. So they analyzed, I think, over 50,000 recipes to understand which ingredients co-occur with each other in popular recipes. And so this was one of the networks that they used in the paper. Each node here is an ingredient. And if two ingredients co-occur in a recipe, in the data set, you have a tie between them. And the frequency of how often they co-occur is the strength of the tie, so how bold the tie is. And again, just by looking at this plot, you can, again, quickly see that there are cultural differences in these clusters, right? So there are some, like for example, this is a completely disconnected cluster here of what seems pretty dominant in North American cultures, but it's very different from, say, the East Asian cuisine. And then interestingly, you have crossover elements, right? So you think something like garlic is a crossover ingredient in these three different cultures. And again, so what's the point of doing this? It helps you understand recipes, but more importantly, it helps you infer what to put in new recipes, right? So if, for example, you take a dish that's predominantly North American and you want to adapt it for an East Asian cuisine, maybe you want to pick something from that cluster, right? So this is again a good example of how a novel network representation of something that is not network, right? It's just a recipe. But creating a network representation, you can get great more insights. So I want to pause here for a while, show you all these different types of networks that we discussed. And so one of the questions that is worth thinking about is, even though these networks are from very disparate contexts, what might be similar or what might be different in these networks? And how do we start to measure or quantify some of these differences? All right, so that's I think something to think about. So let me pause for a second, and any questions or discussion points or something that you want to bring up? Sure. Yeah. So what the study shows is that the Slime-Moore network actually mimics the existing Tokyo Rail network in certain key properties, right? And then the assumption being that the engineers who build the Tokyo Rail networks considered redundancy as a key factor, right? So they would have preferred shortest paths because of cost of construction and things like that. But then there could be other considerations, of course, right? Like this, terrain might be too difficult to do, and that might. But I think the fact that to answer your question directly, shortest paths in a transportation network is generally a key consideration. So probably factored in the decision that went into making the rail network. Yeah. So it's the other way around. So the way the Slime-Moore actually works is it first tries to create a wide mesh of all kinds of ties, and then over time it prunes the non-redundant bits so that only the strong ones remain. So in the paper, read the paper, the researchers then built a model of network formation mimicking that heuristic. So they tried to build a model that first indiscriminately forms links and over time prunes the ones that are non-essential. And again, this is just one way of network formation. We'll come to information later, but you're right. There are now more sophisticated ways to construct networks. But this is a fairly low-cost way of networks. Any more questions? Or feel free to stop me just at any time. Okay. Yes. So I think the question here is, how do we start to think about quantifying these different networks? Like, how do you test if these networks are similar? So I think in the previous session, you've already learned about things like centrality measures or how to compute network centrality measures from a network. So this just to kind of revise that. One way of thinking about network structure is to think about how do you quantify the node positions in a network. So the nodes have characteristics. So in social network, they could be you have gender, you have age, you have education. Those are node level attributes. But you can also have network dependent attributes of those nodes, right? And that's where I think things like centrality measures are useful. So I think the most common centrality measure I would assume is degree, which basically means the number of connections you have, right? And then if it's a directed network, then you can split the idea of degree into in degree and out degree. So like how many connections are incident on the node versus how many connections are incident out of the node, right? Or originate from the node. And then if you represent a network using this kind of adjacency matrix, where your rows and columns are nodes, if there is a link, you have one. If there's no link, then you don't have any value here. In this case, the out degree of the node, so it's an out degree of C, this node here, is basically the row sum, right? The sum of the row. Because it's from C to B, C to B, C to B. And then the in degree of C would be the column sum. So from like how many nodes to C, right? And so you can compute in degree and out degree separately. So this is to one very simple but very efficient centrality measure that you can compute. Efficient computation. You can actually compute this measure very quickly in a large network. There are also other measures. For example, I don't know if you've heard about closeness centrality, which is a measure of how far a node is from every other node in the network. Okay, so think about a social network. Take any one node. Let's say you take I, right? Your node I, and then your denominator here is the distance of I from every other node in the network, every other J in the network, and the distance here is the shortest path. So then you can see here, so it's the inverse of that. So which means that a node that has high closeness is a node that has a large number of shortest paths very quickly to other nodes in the network. Right? So this is generally a measure of reachability. So if a node has high closeness, you can actually start from that node and reach any other node in the network very quickly. Okay. And then I think there's another interesting measure called betweenness, which tells you, which gives you a sense of how many shortest paths in the network include that focal node, include that particular node. So here, if you see, if PST is the total number of shortest paths between any two nodes, then PST of I tells you whether the shortest path includes the node I. So think about it, right? So take every pair of nodes in the network and think about how many pairs, how many shortest paths between those pairs of nodes include the node I, and then normalize that with total number of shortest paths in the network. So again, this is conceptually what this is doing is it's telling you if the node actually sits in the middle of many shortest paths in the network, right? It's kind of like a broker, right? In social networks, you have this term called brokerage. So it's connecting two very dissimilar parts of the network. So one thing that you notice with degree, closeness, betweenness, they are capturing different aspects of the network. So a node with high degree is maybe like a popular individual. I have a lot of friends, so I have high degree. A node with high closeness is someone who's well connected, right? So I can quickly connect to someone through multiple hops. A node with high betweenness probably has high brokerage potential, right? So I'm holding a strategic position in the network that connects two dissimilar clusters. They're all capturing different aspects of the network. So what I want to highlight is, if you're given a network, and if someone asks you, well, which is the most central node in the network? I mean, the answer almost always is it depends on what do you mean by a central node in that context. So if you're studying like a popularity network, centrality might mean, I mean, a good measure of centrality might be degree, because you want to know who the most popular person is. But if you're studying like, I don't know, the spread of a virus, then maybe closeness might be a better measure because you're more interested in visibility, right? So I just wanted to illustrate this particular network where we have multiple nodes that are highest in centrality depending on what measure you're looking at, which is perfectly common. And again, this is not an exhaustive list of centrality measures, right? 50 different centrality measures. There's a very nice package in R that you can use to compute these entire portfolio of centrality measures. I'll send that to you after the talk as well. The common one being degree, it's very easy to compute, right? The other advantage of computing these measures is that you can then think about combinations of these measures and what that actually denotes, right? So if you have a node that is high in degree and low in closeness, it has a certain profile in the network. So you can profile nodes in the network based on combinations of these features. And it is just a very simple illustration, but you can have more complex combination of features. But it's just to say that there's clear interpretation for some of these node measures if you take in combination. So this is one reason why node measures is used. So far, I've kind of discussed the idea of structure in a very static fashion. Right? So given a static network, these are things that you can quickly compute, right? Very easily. But then I think the more interesting question is about dynamic networks. So how do networks even form over time? Like what kind of processes going into the formation of networks? I think it's a very interesting topic. So let me start with a simple illustration. So I've actually picked this story from a very famous textbook and I've modified it slightly to make it easier to understand. So imagine you're at a party, right? Like a networking party, or in summer school, you're meeting each other for the first time. So imagine you're at a party with around 100 people. Few of whom know each other. So it's like a good setting. First day of summer school, you're all meeting each other for the first time. Now, over time, you see pairs or groups of 3 chatting to each other. Right? That's what happens in a network. So you walk up to someone, you say hello, and you talk for a while. Right? So over time, you see like these groups of 2 or 3 people scattered around talking to each other. And then, over time, these groups change. Once you say hello, you move on and say hello to someone else. That's how the networking eventually works. Now, this is the intervention. So exactly one person, X, in the party knows something really uncharitable about you, like a nasty rumor. Exactly one person. So this is the question I want to pose. So by the time the party ends, how many people at most might know about this rumor, and then assuming that everyone gets chatty up. So anytime you meet someone, you spill it. If you know the rumor, you share it with the person you're talking to, and then that person knows it, right? So, but then no person speaks to more than 100 people. This is key. Right? This is a key assumption. So imagine you go to a party, it's 100 people. Among those 100 people, one person knows something terrible about you. And then you go and talk to people, you mingle, but you don't talk to more than 1 or 2 people at any point in the party, right? So at the end of the party, you've only spoken to on average 2 people. At the end of the night, how many of these 100 people do you think would know that rumor about you? And thinking about this question actually is pretty key to understanding how networks form. And take a guess. If you don't know the answer, you're probably not going to figure it out. But intuitively, in this kind of a situation where every person is just talking to 1 or 2 people at the party, how many people would know the secret out of this 100? Let's take any number. What's that?
All of them.
All of them? Yeah, depends on it's a safe answer. Depends on what?
Depends on the people. Depends on the people who knows your rumors. If the people have trust everyone, because people can trust to more than 1 to 2 people, maybe this people is a kind of like have a very high degree centrality, and everybody talk to him, and he also have the rumor about you. Mm-hmm. So maybe if this kind of people know the rumor about you, that means everybody will know your rumor. Sure. But yeah.
Okay. Yeah. So to summarize what you're saying is, if there's a person very high degree, mm-hmm. and that person knows the rumor, yeah. then it spreads very quickly and everyone gets. Yeah. But I've made an assumption here that no person talks to more than 1 to 2 people. Which means there's no such person in the room. So there's no high degree person in the room. Every person's maximum degree is capped at 2. So you only meet 2 people. There's no situation where a person is talking to 200 people or 100 people in the room.
How long is
You could use a very reasonable assumption for that, like you get 3 hours. That's a good point, yeah. Yeah, but I mean, there cannot be subgroups because you only speak to 1 or 2 people. So yeah, the group size would be like capped. Would be like 2 or 3.
what happens for 25 people talk to each other, different categories. One of my
Possible. Yeah. Yeah. So I mean, yes, you're right that there could be a specific context where the viewer just like the guy who knows the rumor just sticks to one corner of the room. It so happens that the person who knows the rumor also doesn't want to talk to anyone in that part. It's possible, but in the general case. All right. So before I tell you the answer to that, let me show you this really nice visualization of how networks form at random. So let me see if I can click this. Can I open this? Yes. Okay. All right. So what this network actually, this simulation shows you is it's our network forms over time, and yeah, we need to wait for the ad to finish. I'm not endorsing SK2. Right? All right. Yes. Okay. So this is a nice simulation of how a network. So this is a network that's forming at random. Okay. So the 2 nodes at every iteration that's forming a link with a certain probability p. Any 2 nodes, pick 2 nodes at random, form a link with a probability p. Do not form a link with a probability 1 minus p. That's what's happening here. Okay. Now I want you to pay attention to this number at the top left here. And you can see this number, this 0.0506. This is actually the average degree. The average degree is at this state of the network, what is the average number of connections that a node has with another? Right? So the average degree is fairly low. And then if you let the simulation run, you see more and more nodes getting linked. Right? And keep an eye on that average degree number inside the parenthesis. It's increasing. And then notice something interesting happens after that average degree number crosses 1. See if you can tell. Dramatic news. Something, I mean, the color changes, which is really interesting, salient, but okay. So do you notice something interesting happening the moment the average degree crossed 1? Right? What happened? Right? So you kind of see like what we call in network a giant component emerging here, right? And then once this giant component emerges, then if you keep playing it, you notice that it gets fully connected really quickly. All right. So this is what I wanted to show you from there. And so then if I go back to this question that we were discussing here, right? So that you're interacting with people at random. So there's a very famous finding in graph theory that in a network, if the average degree exceeds 1, that's a condition for a giant component to exist, right? Which means that there will be almost all the nodes in the network would be part of one connected component, which creates a path in theory for anything to spread, right? So if you have to answer, you have to fathom a guess of this question, you should say close to 100%. Because of course, there's going to be some isolated node that won't be connected to the giant component, but at least there's going to be a path for the rumor to spread once the average degree, which means the average number of people you speak to crosses 1, which is where this assumption is important, right? So even if you just speak to one person on average in the network, there's a chance that something might spread, right? And this has very important implications for things like public health, how things spread, like viruses spread. So here, this is like a summary of what we just discussed. So the scale over here is your average degree. Till 1, and this is the number of nodes that are connected, that are part of your connected component, right? So it's pretty low. Then your average degree is 1. And then once your average degree crosses that particular threshold of 1, the network gets connected very rapidly, right? This actually in physics, this is called a second order phase transition, right? It's a very rapid connectivity of the network. And then for average degree greater than natural log of n, where n is the size of the network, it's all fully connected network, right? So this is just to keep in mind that for very low average degree, you can have a fairly well-connected network. That's the point that I want to highlight. So that network that I just showed you in the simulation is what's called a perfectly random network. It's called an Erdős-Rönyi network, ER network, because the links are formed based on some random probability, right? However, we know that in real world, we don't form ties randomly. There's always some reason or some mechanism following which we form these ties. So I think one of you mentioned that partly you don't go randomly talking to people. Maybe you want to speak to someone you have some familiarity with, or you speak to someone who looks like the person wants to talk to you, and maybe there's some people you don't want to talk to, right? So there are certain rules, social rules that we follow while forming ties. And based on what mechanism you follow, you can actually end up with more realistic network structures that are not random networks. So there's a small world network, there's scale tree, and other kinds of network structures. These are the most popular ones. And each of these network structures are characterized by certain underlying properties, properties that define what these networks are. So for instance, small world networks, and you might have heard of this 6 degrees of separation concept, right? The small world networks are networks that have large clustering and low average path lengths. So those are the two properties that characterize small world networks. Scale tree networks are characterized by the presence of hubs. These are large, high degree nodes. So you have a lot of, not a lot, but you have quite a few number of hubs, and then you have these spokes, right? So it's like hub and spoke kind of a model. So based on what kind of network formation mechanism you use, you can generate these different kinds of network structure. All right. So now, once you have these network structures, and you have, so these are individual actors. So as I mentioned, they form these ties based on various mechanisms, leading to those kind of emerging structures. Right? So this is one way of this one side of the cycle. But then once you have those structures, the network structures themselves constrain behavior on these actors. So what this again simply means is you form your social network based on the ties that you form, but then your social networks influence or affect your behavior in different ways. And again, this is, even intuitively you can understand this, right? Like your behavior is affected by, say, the behavior of your friends. But then you choose your friends yourselves. So it's like a cycle, right? So individual actors interact and create network structures create individual. And this is like a cycle. And a lot of my research is actually focused on analyzing different aspects of this cycle that we have, the individual, the micro to macro. So before I get into that specific problem, I want to quickly highlight that there are also limits to the power of net, right? So I'm quite evangelistic about networks, but I have to acknowledge that there are certain limitations or challenges that I have to take care of. So yes, our network affects every aspect of our behavior, but there are two critical limitations to this, something to keep in mind. So the first is, what psychologists and philosophers talk about in this field of bounded rationality. And again, in very simple terms, what this means is, yes, all of us have a social network, but how much of that network is visible to us at any given point in time? Or even not invisible, like how much of the network is accessible to us cognitively? All right. So let's take a simple example, right? So do you know your second degree friends, for instance? Right? So you know who your friends are, hopefully. And do you know who their friends are? If you do not, I mean, you might have some curiosity, right? You might know that in university, I know A, but A definitely knows B. But in a broader sense, it's harder to do. And the further you go in terms of distance, the harder it gets to infer whether you know your network or not. Even for first degree friends, and this is an do it as an exercise here. If I just ask any one of you, can you tell me the names of 10 of your closest friends? You might have to think for a while. You probably have one or two names off the top of your head, but then after that, you have to really think about who do I name, and then you might end up naming people who are really not close friends with you, just that you thought of them quicker than others. So there are all kinds of accessibility biases when you have to think about networks. And then, so we cannot act on information that is objectively there, but we cannot cognitively access, and we need to make a decision. Right? So sure, your best friends are influence your behavior, but if you cannot think of them when you're making the decisions, then how important is the network, even though it exists? Right? So there's this called bounded rationality. We cannot make decisions based on something that we cannot access cognitively at the time of the decision. So this is one limitation that, so network scientists like myself, we tend to conveniently ignore this, right? We believe that, okay, there is a network, we can use that to predict someone's behavior. Yes, but is that person really using the network to make that decision? We don't know that, right? That's a tricky question. And I think the more interesting is sometimes you have, actually not cognitive, but biological or lifestyle-related constraints on your social network. So for instance, you might have 2,000 friends on TikTok or Instagram, but can you cognitively hold that size of a friendship network? Do you even identify these users as individuals? So there are studies that show, for instance, that we have a biological limit on a stable group size that we can maintain as human beings. So I think, and this is a controversial area of work because some who propose that it's correlated to the size of your brain, to the size of the neocortex specifically. There's folks who say that no, it's not the size of the brain, but it's related to things like dietary behaviors, what we eat, nutrition. But the basic idea is we cannot maintain stable relationships beyond a certain size. You can't have 50 very close friends. It's not possible. So even though you might have a network that's really large, a very small part of the network might be activated when you have to make decisions. Again, it's a very complicated area, but I want to highlight these two as potential limitations for some of the network studies that I'm going to show you next. Okay, so I'm going to pause here. Do you have any thoughts? So I think in some of the early studies in networks, we used small networks where we actually put people in a lab and ask them in a nomination process that, okay, tell me 10 of your closest friends. And they went to those 10 friends and then asked them. confirm, right? And create. In those kind of small network studies, this is not a big problem because you are explicitly recalling those friends in the process. I think this is a bigger problem in the kind of studies we do today with large online networks, for instance, where we assume that, okay, if you have 500 friends on Facebook and you're making a decision, your decision is being affected by some subset of those 500 friends. And again, you're right, I can profile links to those 500 friends based on some trust measure or any other attribute that I have. But I still wouldn't know if the person made that decision based on those connections, right? It's just from the researcher's perspective, I assume that all links are available to the person at all times, which is a very strong assumption. Okay, so how much time do we leave on time? So the final part of the presentation, I want to talk about one specific problem that I kind of led up to so far, which is the idea of social influence, right? So in very simple terms, this is what social influence basically means, right? So you come back to that network I showed you earlier, simple illustration of a social network, a small network. And then if I pose this question to you, right? So if Diana over there votes for a certain party in an election, votes for party A, what is the likelihood that Carl, who's connected to Diana here, will also vote for the same party? But this is a classic question of social influence. So if the node A behaves in a certain way, and I have a connected node, what is the likelihood that the connected node will also behave in the same way? All right? So this is social influence. So first question, and the sub-question, should there be any association to begin with? And why do we believe that there should be some association? Second, if there is a significant association, where we do see that their behaviors, their voting patterns are similar, Carl and Diana, can be attributed to the fact? Can we say that, oh, their voting patterns are similar because they are friends? Maybe it's just random, right? Purely by chance. And then, of course, if this is true, so if you know that, yes, their voting patterns are similar because they're in a relationship or they're friends, it's part of a network, what can we do with that information? Can we act on it? It makes an interesting, and I'll show you an example of where this is important. All right, but this is broadly the problem of social influence. Now, this social influence is obviously, you can imagine, it's very, very useful. For instance, in marketing, you might have heard about this term called word-of-mouth marketing, which is again a very popular way that advertisers and companies use to market their products. And there are multiple studies which point out that word-of-mouth marketing is more effective at driving purchase intentions than traditional marketing methods like ads. So what this means is that customers generally prefer to believe other customers than the marketers or the companies. So this is a good example of social influence. In policy making, in a very recent area of work is on using peer-based interventions. So, like for instance, if you want to run like an alcohol cure campaign, right? So helping recovering alcoholics recover quickly. There are studies which show that having a peer support group can help alcoholics recover quickly. So even in these kind of policy-related contexts, the idea of influence here, peer influence, can be a very strong driver for whatever behavior you're trying to achieve. Okay. In literature, there are a lot of different contexts spanning academic disciplines where social influence has been studied. So in some of my own work, I looked at how social network structures affect content generation. So how your friends affect your posting behavior on social media. In economics and marketing, the researchers have looked at how social networks affect product adoption or service adoption. In public policy, public health, the studies looking at how alcohol consumption, smoking behavior, other kinds of substance abuse have peer effects. Right? So if you start smoking, maybe your best friend starts smoking as well. And so again, it's spanning different fields like information systems, communication studies, economics, finance, public health, you name it, any discipline, you have topics related to peer influence, social influence, which is why I think it's important to discuss over here. So I want to kind of also formalize mathematically what this problem is of social influence. Now, if you have some exposure to causal influence, causal inference problems, you know that this is like a good example of the intervention, right? So you have an individual A, and you're intervening, you're treating the individual A on some attribute or behavior, and you're then just observing their outcome on different behavior, different outcome, right? Let's take an example, and this is from an actual paper. So, for instance, you want to give a literacy training program, so it's related to crop insurance to farmers. And the idea is that farmers who get the crop insurance literacy program are able to better manage their crops. So you give this intervention, this treatment, this policy intervention, this training program to this particular farmer A in time period T1, and then you observe what happens. So also to two farmers A and B, same training program. And then the next time period, you find that farmer A purchases the crop insurance, farmer B purchases the crop insurance, which is a desired behavior that you want to achieve. So this is a classic causal formulation, where you want to test whether giving the insurance training program to a particular farmer leads the farmer to a desirable outcome. And then you would have a control group, right? So you have farmers who you do not treat but are similar to these farmers. Right? And you see if the farmer who does not get the training program does not buy crop insurance. Great. This is standard causal influence training. Now let me complicate this a little bit. Now there are studies where you want to study the indirect effect of intervention on the second farmer, even though the second farmer is not intervened. So that's just indirect. See the same example. So now in period T1, you give farmer A the crop insurance training, but you do not give farmer B the crop insurance training. But then period T2, you observe the same outcomes. You see that both farmer A and farmer B buy crop outcomes. However, there's an additional piece of information here. So you know that they are neighboring households, they're connected in some way. So what I'm trying to test here is if this is the causal pathway that exists. So you intervene on a particular node, and that node's behavior changes. So that's a direct effect of intervention. But maybe the node also affects a neighboring node. And so then you have an indirect effect of it on the neighboring node. And so this part over here, this arrow over here, is the peer influence effect that you have to estimate using a model. Right? So this is what I'm chiefly interested in. Questions or what? Is this formulation clear? So this is also, you can take this is one outcome, right? So this also intervene. Farmer may also affect other behaviors. Farmer. In any study, you're really interested in one of the key outcomes. Yep. So the idea is that what's in direct effect of intervention of farmer B, where path A B exists, there is a link, either direct or indirect. All right, so what you notice in a data set, if you're working on a study, this is very common. You find that in a network, so if there's a path between nodes, you find that their behaviors are correlated. This is standard observation. All right, so in a social network, if you have best friends, their behaviors or lifestyle choices are likely for you. You observe this, all right? But then can we jump from that observation to then saying that, oh, this is peer influence? So if you go back here, if the data set is only this, so you have an existing data set of like a time series data of when farmer A purchased insurance, when farmer B purchased insurance, and you find that both of them purchased insurance at the same time period, is that sufficient information for you to conclude that farmer A influenced farmer B, vice versa? Right? This is a problem. So the battery is running low. So one reason for this is social or peer influence, as I suggested, right? So this is one. This is what I'm interested in. So I want to show that the farmers are influencing each other. But then this is a key challenge, right? So this is what will probably keep you up at night. There are many other confounding factors that could be affecting the same outcome. There are many reasons for why this should be happening. I'll give you a very good example of what those reasons could be. So I've actually taken this example from a paper, it's one of our favorite papers. The reference is below. The paper starts with this question, right? So suppose there are two friends, Ian and Joey, and Ian's parents asked him, so if your friend Joey jumped off a bridge, would you jump too? Right? So the parents ask this kind of question. If your best friend does this, do you also have to do it? Why might Ian answer yes? All right, so two friends, Ian and Joey, and so Joey jumped off a bridge. And then Ian said that, yeah, and so Ian went and jumped off a bridge after Joey, right? Under what conditions would that happen? Look at a classic question of Ian and Joey. Would you follow your friend and jump off a bridge? So the paper says, this paper, that there are multiple reasons for this to happen, right? So this is the first reason. Social contagion or influence. So maybe Joey's example inspired me. So I saw someone doing something crazy, I felt inspired. I don't think something to do it. Right? So this is social influence. This is what I'm interested in. But there are many other many other reasons why this could happen. Okay? So there's another reason. Again, from the paper. Joey infected Ian with a parasite, it suppresses fear of falling. Right? So this is like a biological knowledge. Right? It sounds crazy, but it's plausible. Right? You can't rule it out. Not plausible, possible. You can't rule it out, right? So you get injected the parasite, you don't feel that it's a dangerous thing, you won't do it. It's biological contagion, not social contagion. Here's another compounding factor. So maybe Joey and Ian are friends because they have a shared fondness for jumping off bridges. Right? So they became friends because they bonded over this shared fondness for jumping off bridges. So this is what social network folks call observed homophoby on the focal behavior. So the focal behavior is jumping off bridges, and it's homophoby because they became friends based on similarity on that behavior. Right? Any other compounding factor? What's that? Monetary incentives. Would that be one? Would that be one? Social influence? Maybe not. I mean, I think he's pointing to like a direct economic incentive. Like I'm paying you to do something on self-funding. Yeah. So that's possible. Yeah, I mean, I would still call it some kind of influence, right? So you can attribute it to the other person, right? Maybe you can call it economic influence or something. Yeah. And any other reason? Bridge is burning. Yeah, it's there somewhere. So, yeah, when bridge is burning, people have to jump. The timing is coincidental. Right? And okay, so here's another one. This is again getting a little bit antique, but maybe Ian and Joey became friends through a thrill-seeking club whose membership rules are publicly available, right? Which means that you know that they are members of that club. The researcher knows. So this is homophily, but not on the focal behavior. It's homophily on the secondary behavior. So they are club members, right? So it's not linked to jumping off bridges. Something else that's correlated. So maybe one of the club activities is, okay, this week you need to go to a bridge and jump, right? So this one's very challenging to uncover. This is, again, Joey and Ian became friends because of the shared fondness for roller coasters, which was caused by the common thrill-seeking propensity. So what this basically means is there's no homophily on observable behavior. They became friends because there's something about their attitude or preference, which brought them closer. So it's nothing observable. It's just something inherent to their character. So this is called unobserved or latent homophily because it's homophily based on something you can't see, the researcher can't see. Right? And then the last one is like what Shivani mentioned. Maybe they realize the bridge is going to collapse. And so both of them have to jump. It just so happened that one jumped before the other. It's just coincidental. So this may look like an academic exercise, but what this really points out is you can never be sure that any correlated behavior can be attributed to just direct social influence. There can be all kinds of other confounding factors that you have to deal with. So a big challenge in this stream of literature is essentially proving that, influence is separate from all the economic factors. Right, so that's the problem. This is an area that I have done some work successfully and unsuccessfully. I'm going to show examples of both. There are some potential ways to deal with this problem. How do you isolate social influence from all these other confounding factors? So the gold standard, of course, is do an experiment, right? Randomize people into different groups, expose them to treatments, and then see if they behave differently. So there are two kinds of randomization that you can do in network studies. The first one is arguably the tougher one, which is called network randomization. And this is tough because what you're doing here is you're randomizing the network structure. So you're assigning people to different network structures. So you can imagine that this is very difficult to do in any general context. So there might be stylized cases where you might be able to do this. The other example is what's called treatment randomization, where you keep the network the same, but you assign different treatments to the nodes in the network. All right. Now, the difference between these two in terms of design is the first one is what's called an outward-in design. So the nodes remain the same. The neighboring peers, the network changes, and you try to estimate the effect of the network inward on the node. The treatment randomization is an inward-out design. So where the network remains the same, the nodes change their behavior, and there's an inward-out influence from the node to the network. All right? So there are different contexts in which you might be able to do. Both are stylized, very hard to do in the general case, but you might get cases where you might be able to run some of these things. So there are concerns with running experiments on networks. The first one, of course, is selection concerns. How do you assign treatments to nodes? And maybe the nodes that get the treatment are different from the nodes that do not get the treatment in terms of their peer effects. Right? Because the network is also evolving in parallel, right? So it's not just because of the treatment. So there might be some selection concerns. The second one is also very interesting. It's called network interference, or sometimes called treatment leakage. Again, think about it. A network by design is connected. So can you have like a clean separation of treatment and control group? Probably not, right? So can you guarantee that the treatment group nodes are not going to spill over the treatment to people in the control group because they're all connected? So you cannot theoretically guarantee that there are ways to correct for this, but this is a big issue in network studies. And then, of course, this is another concern. Like, even if you're able to sample nodes into treatment and control, you have to guarantee that the network structure is comparable. Otherwise, the network structure itself becomes a confounding factor. So what the treatment and control group have different network structures, and that's confounded with the treatment. Right? This is another concern. So, how do you solve this? There's one way to address this problem is what's called mechanism designs or mechanism experiments. And this, I think, is a very clever way of doing it, where instead of changing the networks, right, or instead of changing the peers, you manipulate or change the view of the network. So if you change how the individual nodes access the network, you don't change the network. So let me show you an example. There was an actual study where researchers at Facebook wanted to see if having more friends liking a Facebook page increases your likelihood of liking a page. Now, how would you do it in a pure experiment, right? You incentivize someone's friends to like a page and then see if that affects the person's liking behavior, which is impractical. You can't pay people to like Facebook pages. So there is something interesting. So they use what's called a social cue. So this is an ad for a Facebook page they showed Facebook users. Now, if you notice in the first copy, they just mention how many people have liked this Facebook page, right? In the second version of the treatment, this is called the social cue. Instead of showing the number, they showed how many of their friends have liked the Facebook page. So this serves as a social cue. So here, you're not changing anything. You're selectively showing the person a certain view of the network and seeing if this changes their brain. And they actually found that showing a social cue increased their likelihood of liking a Facebook page. So this is one clever design. This was a very famous study that came out in 2014, created some controversy, not because of findings, but written down. So researchers at Facebook and Cornell, they wanted to study if happiness as an emotion, a mood, can spread through Facebook in a controlled fashion, right? So prior to this, there were studies that had uncovered that happiness is also contagious, but in face-to-face interactions, right? But there was no study that had investigated if happiness or emotions broadly can spread digitally without face-to-face contact. So this was one of the first studies to empirically test that. It was a massive experiment. So they randomized around 690,000 online users, Facebook users, into 3 groups. And this was the treatment, right? So I don't know if you've used Facebook, but you have the news feed where you see posts from your friends. So they filtered the news feed of these different user groups to suppress either positive posts or negative posts or none. All right, so this means you log into Facebook, but now you see fewer positive posts from your friends. Or you log into Facebook and you see fewer negative posts. So there's a positivity reduced condition, negatively reduced condition, and a control group. And the hypothesis was that people who see fewer positive posts will end up posting fewer positive posts. People who see fewer negative posts will end up posting fewer negative posts, right? So that's emotional direct contagion. Right? So you see positive things from your friends, you post positive things. You see negative things from your friends, you post negative things. Now, another reason why they did this study was also to test cross-contagion, which means that sometimes on social media, if you see that your friends are really happy, you feel sad about your life, right? And you might end up posting sad stuff. So that's an actual hypothesis, right? So you might have cross-contagions. You see positive stuff, you end up, complaining about your life and worrying, oh, my life sucks. If you see negative stuff, maybe secretly be happy about your life. Like, I didn't do that in my life, and it kind of shows in the post that you post afterwards. So this is what they found. Again, and this is an example of a mechanism, right? Because you're not changing your friendship network, but Facebook cleverly filtered the news to change your view of what you're seeing from your friends. And you can see why this was controversial, right? So there's a lot of outrage. But this was at the key finding, right? So in the negativity reduced condition. So this is the percentage of positive words and this is the percentage of negative words posted by the user. So users in the negativity reduced condition, so this is the experimental group, this is the control group. In the negativity reduced, in this case, they saw more positive content, produced more positive words and fewer negative words. And those in the positivity reduced condition, so they saw more negative content, posted fewer positive words and more negative words. Right? The effect size was very small, right? So it's not that small. I think they argued that even a very small effect size for a network as large as Facebook translates to actual impact. Right? And so this was a study, interesting and highlights that what you can do using mechanisms. So there was another study, again, similar mechanism design, where they showed that by showing voting triggers on election day, you can get more people out to vote. So again, on Facebook, right? So on voting day, when users logged into Facebook, they saw one of these 2 conditions. They saw a banner showing that, click this link to find your nearest voting center. And you can click this button to indicate to your Facebook friend that you're voting, or some kind of signal. This was an information condition. And there was a social condition where you had the same voting center link, the I voted button, but in addition, you had the banner with social cues. So you saw how many of your friends have clicked the I voted button. And I think they found that people who were exposed to the social message conditioning were like 3% more likely to click the I voted button as well. And I think in the US, a lot of voting records are public, so you can also correlate that with see who actually went out and voted. You can match names on Facebook with voting records. This is a pretty good study. Another example of mechanism designs. Network remains the same. You only change what you get to see. Yeah. Right? So this is a very popular way of designing experiments on networks. Okay, here's the second one, the second solution. This is one of my favorite research methods, and this is called natural experiments. Right? And so natural experiments are, as the name suggests, these are experiments which you do not do. Right? So you don't randomize, like nature does it for you. So there might be contexts where users might get randomized into groups just by pure chance. Okay, and that's opportunistic because it rarely happens, right? But when it happens, you can use that to study different outcomes. So I want to show you this very interesting paper from our Ph.D. advisor. And he studied the impact of hurricanes in the US in 2008 on how people's Facebook friendship network changed after the hurricane. And I can give a bit of context. So in the US, when there are major hurricanes, you actually like leave your college dorms and you go and live with others. There's actual movement of people during these disasters. It's very different from like Hong Kong or Singapore, where you don't have to leave your homes anymore. So the context for this is Hurricane Ike in 2008, which at the time was the second most expensive hurricane in US history after Katrina. And it started over here. It was on Louisiana, Texas, and it spread inwards and then died out around Michigan. And I think what the researchers wanted to study was what was the impact of the hurricane on the friendship network of students in the impacted area. Okay? And this was a design that they used, which is very clever. So they collaborated with Facebook, and they found users belonging to affected universities in the region. So these are universities that are located right at the kind of the place where the hurricane made landfall. So these are the most affected universities. And then they had a matched group of universities that are similar to this, but were not affected. All right, so these are 10 universities that are similar to these 5 universities in terms of university level factors, but were not affected by the hurricane. And then had a broader list of other universities that were both not similar and not affected. Right? And this is what they found. They actually showed that, so this blue line here is when the hurricane struck, right? This is degree. The red line is the treatment group. So these are users who belong to the affected universities who study there. The blue line are students who belong to the unaffected or similar universities. So you see that there's no change in degree before and after the hurricane, which means that, I mean, just by looking at that, it implies that there's no change in the number of friends that you're making between the treatment and control group. But something interesting happens when you look at transitivity. Transitivity is, it gives you a sense of triangles in a network. If A is friends with B, B is friends with C, what's the likelihood that A is also friends with C? So the probability of pointing out that their triangles exist. So this shows that the treatment group actually increases in transitivity after the hurricane, but the control group decreases. Right? There's a big gap in transitivity. And there's no change in between this. But if you just take these two in combination, it tells a very interesting story. So it tells you that the treatment group doesn't change significantly in terms of degree compared to the control group, but it changes significantly in terms of transitivity, which means you're forming new friends, but these are also friends of friends. That's why your transitivity is increasing. So the new friends you're forming are helping you to close the triangle. Right? And this is consistent with what happens during a natural disaster, right? Maybe you go and stay in a friend's dorm and you become friends with that person's roommate and you form a triangle. So this is what's happening. So you just look at these two collectively. That's the story. Anyway, I mean, the finding here is not super important, but what I wanted to highlight was this is one way of shocking the network without you doing anything. So here the network changes exogenously, but you don't randomize anyone in any group. This is a perfect example of a natural experiment. And then you can see how the network change that you observe here affects any other outcome. So the network changes naturally. Right? This is another good design. And of course, there's studies that use network randomization techniques. Right? So this is a good example of that is what's called cluster randomization. So if you have a network, as I said, it's very difficult to have a clean treatment control split. But what you can do is you can use natural partitions. So for instance, I don't know if you know this, but back in the day, many tech companies would launch their features first in New Zealand because it serves as a natural partition for the user base. Because the users in New Zealand are English speaking. New Zealand has like a 5 million odd population, which is a big sample size. And they found that in terms of their communications, they mostly communicate with people within New Zealand or maybe Australia. And the links to other parts of the world are relatively limited. So it serves as a natural partition for doing a treatment control scheme. So New Zealand becomes the treatment group, rest of the world becomes your control group. Right? You can also do it statistically, right? So you can uncover clusters and then assign entire clusters to treatment or control groups. Right? So in experiments, you assign individual nodes, but you can think of assigning entire communities or entire clusters to the treatment group. So that's another way of. And then you still find nodes like this at the boundary, which has links with both clusters, and there are ways to statistically minimize that risk. And then finally, these are purely statistical approaches that don't use any kind of randomization or any kind of experimental control, purely using structural methods or graphical models. And these are methods that you use when you only have historical data. So you only have observational data. You have no way of controlling anything. You can use these methods to study as well. So with the time that I have remaining, 15 minutes?
Yes, lots of questions.
So I'll wrap it in like 5, 10 minutes.
It's 11:20 now.
Well, 10 minutes, 5 minutes. 5 minutes. So quick summary, experimental methods, great, you have higher control. It's ideal for causal testing because you can strictly control end conditions. Disadvantage is lower ecological validity, which means that there are many things you can't do in a lab. Like, can you randomize friendships? Can you get people in the lab and say, hey, pretend you're friends? That's, you can't do that, right? Non-experimental methods are great for that, right? You can observe what people are doing in the wild. You don't have to like recruit them. You don't have to intervene or anything. But there's heavily assumption intensive, these methods. All right, so I won't get into the details of this method, but this is a method, stochastic actor-oriented models. I will send you some stuff on this after the talk. So there's a link there. This is a very flexible simulation-based method that you can use to model the co-evolution of networks and behavior. So if you have a study where you have some kind of network and some kind of behavior, you want to study the effect of one on the other, you can use this technique. Again, it comes from the same family of methods as exponential random graph models, for those of you who are familiar. But if not, I mean, you can go to the link, there's more information there. But I want to just show you that this is the intuition behind the method. So the way this method works is you observe a network and behavior state at two different, so this is your data set at two different time periods. So you have a network and these shaded or dark nodes are your behavior. So you observe at T1 and T2, right, at T0 and T1. And what this method does is it simulates thousands of microsteps, where at each microstep, you can either make a change in a phi or you can make a change in a behavior, but not both. At every microstep, you make a change in the network, you keep simulating it till it converges to the next observed state of the network. And when that happens, you map out the parameters of the model, right? And then I think the question that the model addresses is, well, how frequent are these microsteps? So there's a way to control that. And then at every microstep, how do I make the decision? So how do I know whether to change the phi or whether to change the behavior? And there's a utility function to control that as well. So I won't get into the details of this in the interest of time, but this is a model that I use quite heavily in my work. And I think if you want to know more, it's a great resource over here. Tom Snyder's page here, who's the founder of this model. So, okay, in 2 minutes, I just want to give you a teaser for some studies that I've done using that particular method. Just one slide teasers. So this is a study I did in 2019, where the problem that I was trying to address was, this is my social network, all right? It's arguably a little larger than this. So I'm here, and let's assume that I have 3 very interesting friends on the platform. So the question I'm trying to address is, what happens to my posting behavior if, say, Mark Zuckerberg and Elon Musk wants to get into engagement, so they start posting a lot, and so what does that do to my posting behavior, right? So this was my question that I want to address. Is there evidence of peer influence after controlling for all these confounding factors? And are these network effects dependent on the level of the posting behavior? Which means, is the influence dependent on how much they post? The heterogeneity in that, right? Second study, similar context. Similar context in terms of model, different context in terms of domain. Here, I'm trying to study academic interactions in the university, how students interact with each other online. So first, I'm trying to ask if students interact with similar others. Is there homophily in who you choose to interact with within a semester in a university? And second, based on that interactions, is there evidence of influence? So does my academic performance influence my peers' academic performance? And then subsequently, does that spill over into your labor market outcomes in terms of what jobs you get or how much salary you earn, right? And then similar to the previous study, I'm trying to study if there these vary for high performance students and low performance students. And we have some very interesting findings there. This is fresh out of the oven. I just finished writing this draft yesterday. Here, we're actually trying to study policy implementation in a social network. So imagine you're a government, you want to introduce a policy, or you're like Facebook or TikTok, and you want to introduce a new feature. You're not just introducing it to a user, the user is embedded in a social network, right? So the policy effect is confounded with the treatment, with the network effect, right? So I get the policy from the platform, but I also learn from my friends. So what I'm trying to do here is isolating the effect of the direct effect of the policy from the network effect, to see if I can do that, right? So there are 2 goals here. So kind of estimating the net effect of the policy, which is the direct effect of the policy plus some network-induced effect, right? And second, to then see if the network helps the contagion or spread of the policy-linked behavior, right? So the way we are doing this is basically to innovate on sampling data. So that's just more information. This is a broader context of what I'm doing. All right, so just to conclude, given the background of the studies, some key insights. Well, I hope I've been able to convince you that studying social networks can lead to some quantifiable gains. But then also there's considerable heterogeneity, right? So these gains depend on the type of user, the type of network, the context you're studying. So you have to really do the study well. And then if this is true, then hopefully network-based interaction might be useful as an early help promote certain behaviors. There are a couple of challenges here that I faced. I'm not going to go into that, but one key challenge that I want to mention here is there are so many layers of social network. You only have access to maybe one. So maybe I only have the social network on Facebook, but I don't know what those users are doing in the real world. So since there are multiple layers of interaction networks, it's very hard to control for all kinds of interaction. That's a challenge. This is a popular review on recent journals. They'll ask you, well, are you controlling for what they're doing outside the platform? It's difficult to do. All right. Parting thoughts. This is my final slide. Hopefully, I've been able to argue the case for the fact that networks are ubiquitous, and this makes them both interesting to study and useful for their context. It's vital to our understanding of what people are doing in a society or in an organization, which is what I want to study. The access to this network data is increasingly engaging by organizations. It's very difficult to get access to high quality social network information, which is why I personally have shifted from studying more relational networks to more kind of creative networks, like interactions or co-occurrence or co-authored with these kind of networks. And finally, hopefully I've been able to give you like a teaser, early preview of work on causal processes on networks, peer influence, and being able to convince you that it's a challenging problem, right? Even if there are no very good solutions, but there are some ways to kind of mitigate these problems, right? So that's what I have for you this morning. Today, I want to be on a joke, all right, on a lighthearted point. This is something that this is not meant as a joke, but I heard someone say this at a conference many years ago in a serious context, but it sounded funny when I heard it. So the person said that there are two kinds of social scientists in this world. The first are those who study social network problems, and the second are those who study social network problems who haven't realized it. So I hope that through this session, I can kind of nudge you into kind of revisiting the problems you're working on and trying to see if you belong to the second kind, right? If there are really social network problems hiding in the problems that you're studying, and to think more about social network problems in the phenomenon of interest. Thank you. A quick shout out to some of my collaborators whose work I've highlighted in this presentation. And yeah, I'll be around for more questions if you have. Thank you very much. That's all.
You also have questions over lunch, you can also do that.
Yes.
Thank you for this wonderful talk. It's quite inspiring. I have a very quick question. As you mentioned, it's quite to differentiate the effects, the peer effects from social network and other confounding. And I believe we have actually encountered many challenges from the viewers about those questions. Can you share with us some of your strategies to actually address this kind of concerns?
Yeah, that's a good question. And a lot of that depends on what discipline you're targeting. In particular, social network is cross-cutting, right? So if you're doing social networks work in economics versus psychology versus social psychology versus social networks as a discipline, you will get different kinds of pushbacks. So I think in economics, they're very particular on identification strategy, right? So if you use a graphical model like the SAOM model, the main pushback would be, yes, but are you able to cleanly identify the peer influence or ruling out everything else? So that's hard to do. For that, you have to do like a field experiment, like a mechanism design. But if you're submitting it to like sociology or social networks, because the field is aware of how challenging it is to do that, they're a little more tolerant of methodological slippage, right? So they might be able to grant you some leniency in how much you're willing to do. But I think the way I try to handle it is I'm always very upfront about these limitations. And so I think I borrow a phrase from Tom Snyder's in the SLM models. In his papers, he calls the SLM model a way to infer restricted causality in that person's behavior, which is another way of saying we can't prove it for sure, but it hints that there might be some causal relationship. But what you can do at the very least is you explicitly estimate influence and homophily. And by doing that, you at least reduce the bias in the influence estimate. So the more confounding factors you estimate, the more bias you reduce from the estimate. So at least if you do that, I think that's still a good conclusion.
Thank you. Thank you for sharing.
Causality sounds like sparking correlation.
Yeah. A restricted take on causality. This is a restricted take on causality. Yeah. All right. Yeah, great. Thank you very much.